Hi, good afternoon, good morning, or whatever. So, welcome. So, I'm going to give an overview of our work on cloud confidential computing, covering both our research in Cambridge and also our collaboration with Azure. So, I haven't given lots of details about recent attacks, but it should be quite clear by now that we should take data breaches seriously. You can look at SolarWinds, you can look at more recently the colonial pipeline issues to see that the more we depend on advanced computing infrastructure and specifically on the cloud, the more risk we are taking with our information. So there are many things we can do about that. What we are focusing on is technical mechanisms to prevent those issues by providing stronger security guarantees based on trusted hardware and cryptography. So the general idea is to evolve from computing in the clear, where the data and the code can be interfered with other parties, to encrypting data and operating on it in isolation from the rest of the world so that we can get stronger security. So that's a trend. So it started by encrypting data at rest systematically in backups, in disk, and then encrypting data in transit by making HTTPS or TLS mandatory for all connections. And the next natural step is to protect data while in use on a platform. And so the technology for that is named generically Trusted Execution Environments. And the prime example, the first example of it is IntelliJ, but there are many others that are appearing or that are about to be deployed. So why should we protect data in use? So we have a small application, and it is critical so we keep it simple and so that we can review it. And we upload that to the cloud. That side is going to run together with other applications, maybe from ourselves, maybe from other tenants. It's going to rely on the operating system and the hypervisor, on the CPU and other bits of hardware out there, and also on the host. So it's going to be exposed to potentially a lot of attacks if some of those parties or components get compromised. And of course, in an ideal setting, the application security should depend only on the code that we are seeing and on the hardware that we think we are using, not on the full cloud fabric or its other tenants. So as I say, it's part of a big effort in the industry, starting from the hardware and then moving on to standardization for the software and the services on top of that. So, but we have been exploring that together with Azure Confidential Computing, starting with AGX for many years now. And so IntelliJ is far from perfect, but it has the merits to be first and to enable to isolate a very small part of applications, thereby reducing the effective TCB by quite a lot. So instead of trusting the application and all the software that it involves, plus the hardware underneath, with IntelliJ, you can just trust the CPU, the core, together with the code of the application that runs inside of the trusted execution environment, and ignore the rest of the context. So I'm covering that for AGX, but that's the same for all those devices. The core mechanisms are isolation from the rest of the system, so that only the trusted code that has been loaded can access the data. And everything else, before it leaves the boundary of the trusted execution environment, we need to be encrypted, or when it's read back, we need to be decrypted and authenticated. And these kind of devices are based on hardware root of trust, where the keys are embedded into the silicon. So there is no way to lose the keys unless you actually physically attack the device with very advanced techniques. So the second key mechanism now that we can run in isolation is to actually provide remote evidence that we have loaded a trusted execution environment on the CPU with that particular code and configuration. And that's the purpose of remote attestation that binds the initial content of the TE to a platform certificate issued by the vendor, the hardware vendor at the end of manufacturing. And that can be checked remotely. So typically one will check that the right code and configurations have been loaded into that TE in a TE that belongs to the right data center before releasing keys to start actually processing confidential data. So that's available today in Azure. So my slide is out of date. There are many more regions now where VMs with LGX supports are enabled. And we have many customers experimenting with them and starting to see what they can do with this kind of isolation technology. So there are different ways to do that. Of course, it provides stronger security, but there is also some overhead in terms of usability and complexity. So the most secure, the most controlled way is to use an enclave with a very small system support and very limited interface, but with a TCB, software TCB that is going to be rather small, and that's for that, you can use the OpenEnclave SDK, or that's also what the CCF framework is using. I'm going to present that later. And more simply, you can run existing containers or even existing VMs in a trusted execution environment as a whole. And so that provides a basic isolation, but of course, unless you are careful with what is running inside the container or inside the VM, you are not getting that much security. So you can run your container inside of AGX, and we did that using, for example, AGX LKR. Quite interestingly, in the next generation of CPUs on the server side, you will be able to run a full confidential VMs with hardware protection and attestation, enabling stronger security at a minimal cost in terms of software development. So in this overview, I'm covering two applications. So the first one is machine learning, unsurprisingly, and that corresponds to a series of pilots we did with some customers. So this one is about doing confidential inference with Royal Bank of Canada, and that relies on running Onyx runtime to run the inference on the model, on a confidential model with confidential data provided by the client. Within an AGX enclave. So what's interesting about it, well, first of all, is that we can integrate that with the rest of the services to provide a solution that is secure, even if the rest of the cloud, including the rest of Azure, is compromised. But also it shows that it takes more than deploying the hardware. You also need to integrate it with some trusted services, like a service to delegate attestation, or to manage key release. In our case, it's Azure Key Vault, which is based on HSMs for releasing the keys so that you can start multiple enclaves that will have access to the same secrets. There is also sub-protocols to start and to shut down VMs to provide elasticity. There is also some sub-protocols to release the keys and also to multiplex between the front end that is untrusted and that is forwarding encrypted requests to any of the provision enclave running the model at that time. So what you get out of that is verifiable confidentiality, meaning that the client is guaranteed before it releases its request that it is running on the authorized model within the adequate hardware. And conversely, the model provider is guaranteed that the model is used only for serving those requests. So the other application I wanted to highlight is something that we actually developed in our team in Cambridge, and that is named CCF. So that's a distributed ledger based on a trusted execution environment. So we open sourced it 2 years ago, and we just recently released the V1, which is the stable version with long-term support guarantees in Azure. So what CCF does in a nutshell is very simple. So it provides a key value store where you can bring your own application logic to run inside the secure service. And you can have clients that do RPCs to that service and that access the key value store and the history being encrypted, signed, and replicated inside the ledger to provide auditing and verifiability. In addition, there is a subpart of the service that deals with governance and that is accessible by a subset of clients that are privileged as members of a consortium. And that provides the functionality to run a permission ledger under their control. So they get to decide what is the authorized code for that, or to update that code, when to start and to shut down the service, for example, and when to replace the TEs that are running that service. So that's the nice abstraction. So the implementation, as you can guess, is running on top of trusted execution environments. In the current release, it's using SGX enclaves. And those enclaves are communicating with one another through encrypted channels and communicating with the clients, both the user and the members over TLS channels that are terminated within the enclave. And they are also outputting encrypted authenticated blocks for the verifiable ledger. So in combination with the hardware guarantees, it provides strong integrity and confidentiality guarantees. So in particular, provided a quorum of the replicas of the trusted execution environments are not corrupted at the same time, then we get that the transactions are replayable, so they are correct. From the ledger, you can replay everything from the start. You also have tamper proofing, meaning that once something has been committed, there is no way to remove it from the ledger, unless again you compromise the quorum of the hardware the system is relying on. You have consistency that prevents any forking. And last but not least, we have also the ability to issue signed verifiable receipts that enables anyone to check that something has been recorded into the ledger without having full access to the encrypted ledger, which provides support for independent transparency or verifiability. I don't have time to go into the details, but if you look at the papers, you can see that we take great care to survive the compromise of some trusted execution environments, or even multiple of them, so that even if everything goes wrong, we still have a strong basis to blame some replicas and mitigate the resulting erroneous transactions. For the final part of my overview, I just want to give some consideration about the actual security of confidential computing. So it's nice to have a new hardware, but of course, whether we should trust it or not is highly debatable. What I'm not going to describe, and that is super important, is that all of that comes in addition to the best practice for managing a public cloud. So Microsoft, because it runs at scale, can take great care of running professional teams, monitoring physical security, threat detection, managing patches and the like, in a way that is not affordable, except to a couple of other top players. And in a sense, what trusted execution environments provide you on top of that is a way of, as a user, to get control over the TCP that you are using, but while being able to benefit from this shared effort in the cloud. So of course, the main remaining issues are side channels, because the public cloud is shared with many other users and also with the cloud provider. And so unavoidably, side channels are going to be a lasting issue with this system. And indeed, we have side channels at all levels. So we have them at the application level. If you do machine learning, for example, we do that at the system level with traffic analysis, the use of network, of memory, of caches, and the like, and also at the level of platform. So I'm sure you have heard about speculative attacks. There are many others. There are also very effective low-level physical probes, like differential power analysis, that are going to be really hard to defeat for general-purpose CPUs. So in a nutshell, it means that application security should not be taken for granted because you are running on top of a trusted execution environment, and that requires some care. So in some cases, it will rely deploying specific algorithms like differential privacy. In others, it will rely on selecting libraries that have been hardened against side channels, like using obvious algorithms, or as is the case for crypto now, constant-time programming. And Jonathan is going to give you more details about that. Regarding Intel, I'm sure you have seen many of the attacks. it has been quite challenging, to say the least, with many interesting discoveries and attacks, in as much as the IntelliJ has been the subject of intense scrutiny for many research groups. The situation is not as bad as you might think it, as much as things can still be patched even at the hardware level, at least at the microcode level. And the attestation and the keying provides a way to actually check that updates have been deployed, so you can at least mitigate issues once they have been identified. Also, to our knowledge, no reward exploits have been exercised inside of Azure yet. There are, of course, more algorithmic alternatives, so you can rely on more advanced cryptography. In particular, you can rely on homomorphic encryptions or multi-party computation, which provide sharper guarantees with mathematical guarantees, but you still need to trust some of the parties for some of the computation. So in a sense, the two kind of mechanisms are going to be complementary. As an aside, most of those mechanisms are excellent at providing strong confidentiality, but not so great at guaranteeing integrity. So using TEs for integrity and more advanced cryptography for protecting the core secrets makes a lot of sense. Also to keep in mind, cryptographic approaches, although they provide stronger guarantees, are also much more expensive, from 2 to 7 order of magnitudes, depending on the problem you are looking at. Okay, so there are many papers, but you can go on our website to see the details if you have questions or comments. And yes, we are hiring, so here is a link if you want to have a look at what we are doing in more details. Thank you.